So in this video we want to look at the graphs of circles. Now, as always, we want to start with the most basic representation of this kind of graph and then think about applying transformations to it. Now, applying transformations to the circle is not as obvious as it has been for the other functions. But let's start by having a look at the most basic circle. So the most basic circle is a circle with its center at the origin and with a radius of 1 unit. Okay? We actually call this the unit circle. We talk a lot about the unit circle when we get to some trigonometry later on in the year. Yes, big spoiler alert, trigonometry is really about circles, not about triangles. Okay, so x squared plus y squared equals 1 is the most basic equation for a circle. Now, we're going to talk a lot more about something called functions versus relations a bit later on in this topic. But everything we've looked at before now, we write y as the subject. Y equals x squared, y equals x cubed, y equals x to the power of 4, y equals 1 on x, y equals 1 on x squared, y equals root x, okay? And we use function notation to represent those because we replace the y with f of x. Now, we haven't talked particularly about what makes something a function. We'll talk about that further down the track. But one of the key things is, so we've started looking at using our function notation for our transformation. So if we have 2 times f of x, that's 2x squared. It's a dilation from the x-axis by a factor of 2. If we have f of x plus 5, that's x squared plus 5. That's a translation up by 5. Now, we have all our understandings of how to apply transformations to f of x, and that is for functions when y is the subject. Now, we don't have y as the subject in the traditional way of writing the equation for a circle. So if we want to apply our transformations to the circle in the way that we understand them up to this point, we're going to need to make y the subject of our circle equation. Okay, so when we do that, it's a reasonably simple rearrangement. Y squared is 1 minus x squared, and then we're taking the square root of both sides, so y could be the positive negative square root of 1 minus x squared. And actually what we've identified here is 2 separate functions which describe the 2 semicircles that make up the full circle. So this is y equals, I was just checking whether it's already written there, this one is y equals the positive square root of 1 minus x squared. That's the top half of the circle. And then this equation is y equals the negative square root of 1 minus x squared, the bottom half of the circle. Together those things give this, plus or minus, which can be rearranged back to this. Now this adds in a new complexity because yet we have another function with a square root in it. So you need to be careful about just seeing a function with a square root and assuming that it's a square root graph, which we looked at in the previous video, this one, okay? If it's the square root with an x squared underneath it, it's going to be a circle, not a semicircle, sorry, not a square root function. When we have a square root function, it's y equals square root of, this only has x in it. It might be 2x, it might be x minus 5, it might be 3x plus 5, whatever it is. But there's no x squared under here. The minute there's x squared under there, it's going to be a semicircle. Okay, so we've got our 2 halves of our circles. And the advantage here is now that we have y equals, we can think about those as being f of x, and then we can think about applying transformations in the way that we're familiar. Okay. Alright, so let's think about what we would need to do to change the radius of the circle. So if we wanted to plot a circle on the Cartesian plane, that had a radius of 2 instead, if we think about our transformations, that's going to require us to dilate the graph from the x-axis by a factor of 2. But it also, if we only did that, we would get an ellipse that does this, okay? So we also need to dilate from the y-axis by a factor of 2. So we actually need to be multiplying by 2 in both directions. So as I said, if we were to just stretch from the x-axis, from the y-axis by a factor of 2, we would only stretch the graph out this way and it would become an ellipse that way. If we were to only dilate from the x-axis by a factor of 2, we would only stretch the graph out this way and it would become an ellipse that way. And so we would need to do both dilations to keep the shape still a circle and to increase its radius, to double its radius in that instance. Okay, so if we wanted to, change the radius from 1 to r, we would need to dilate from the x-axis by a factor of r, which means doing r times f of x, and dilate from the y-axis by a factor of r, which would mean doing f of 1 on r times x, or x on r. And so together, doing both of those transformations, we're going to need to turn f of x, which is this, into r times f of x on r. So if we do that to the equation of the circle, now it is a bit not mathematically correct to call that f of x, because it's not technically a function, but for all intents and purposes, for what we know at this point, I'm just going to call it f of x. So if we think about f of x as being the positive or negative square root of 1 minus x squared, then we want r times f of x on r, okay? And so that is going to be equal to, so we're going to, let me write that underneath actually, we're going to do r times f of x on r, which means, let me write them in different colours. That's the dilation from the x-axis, and that's the dilation from the y-axis. So that means that we want to do r times the positive or negative square root of 1 minus, and instead of x, it's going to be x on r, all squared. Okay, so what we actually have is y, it becomes, under this transformation, it becomes y equals that. Now this is r times plus or minus something, so it's not r plus or minus something. So that we could just write that as plus or minus r times the square root of 1 minus x on r all squared. Actually, no, let's not do that. My apologies. Let's just divide the r over to the other side, because I'm going to go back to a format of the equation that looks like this, because that's traditionally how we write circles. Okay, so I'm going to multiply both sides by r, which means we're going to get r times y equals plus or minus this. Sorry, we're not multiplying by r, are we? My apologies. It's like I'm dividing both sides by r, so y on r equals plus or minus the square root of 1 minus x on r all squared. Now, if we were to square both sides of this equation, we get y on r all squared equals 1 minus x on r all squared. If I add that x term to the other side, I've got x on r all squared plus y on r all squared equals 1. This is x squared on r squared plus y squared on r squared equals 1. And so if we multiply everything by r squared, we get x squared plus y squared equals r squared. And so that is the equation of the circle after we've dilated it by a factor of r from both the x and y axes, and hence we've changed the radius to be r. So this circle has its centre at 0, 0 still. We didn't do any translation, but its radius is now equal to r because we've dilated by r in both directions. If we were to change the centre, as I said, we would need to translate. Okay, so let's go back to our circle. If I wanted to move the centre from 0 to 0, 0, 0 up to 2, 3, I would need to translate to the graph to the right by 2 and up by 3. Okay, so we want to think about applying translations to this general function for the circle. Okay, so translating to the right by h units is f of x minus h. Translating up by k units is f of x plus k. So we want to do both those things. We want to do f of x minus h plus k. So if originally our circle is plus or minus the square root of 1 minus x squared, okay, it's now going to be, we're now going to make it, once we do these transformations, it's going to be, we're replacing the x values with x minus h. So it's going to be plus or minus square root of 1 minus x minus h all squared. And on the end, after the function, outside of the square root, we're adding on k. Okay, so again, I'm going to manipulate it back to a more traditional format for us to see the equation of the circle. So we're going to take away k. Y minus k equals plus or minus square root of 1 minus x minus h all squared. We're going to square both sides. Y minus k all squared equals 1 minus x minus h all squared. And then I'm going to add that k bracket onto the left-hand side. So x minus h all squared plus y minus k all squared is equal to 1. And so there is my circle that now has a centre. If we've gone to the right by h and up by k, the centre is now at hk, and we haven't changed the radius, we just did the translations, the radius is 1. So if we combine these two things together, changing the radius and changing the centre, we get this. X minus h all squared plus x minus k all squared is equal to r squared is a circle with its radius at r and its centre at hk. What I want to be clear about is that this doesn't contravene any of our understandings of transformations. Everything we understand about transformations before now, we've just applied here. Dilations at the top up here to change the radius. Oops, sorry. Translations down here to change the centre. I know normally when we go up or down, it's about plus k goes up and minus k goes down. But what you've got to think about is if, oh sorry, that's my fault, that should be a y there. Can we make sure that gets fixed? If we were to rearrange this to make y the subject, we do end up with plus or minus the square root of r squared minus x minus h all squared plus k. Right by h, up by k. Okay. So it doesn't contravene anything we already understand. That's the important thing. We present it in a different way, and so we do need to interpret those things out of it differently. But really you just want to treat the circle differently. You just want to understand it's going to be in this form. X minus something goes to the right, y minus something in the bracket goes to the left, goes up, and the r value over here changes the radius. Okay, so let's have a look at this. We're going to sketch the graph of y equals x squared plus y squared equals 5. So no translations, the centre hasn't changed. The centre is still at 0, 0. R squared over here, so x squared plus y squared equals r squared, is a circle with its centre at the origin and its radius of r. So the radius isn't 5, the radius is the square root of 5. Okay, so it's going to be a circle with its centre at the origin. The centre is an important feature of a circle. Make sure its coordinates are labelled. Again, if it's the origin, it doesn't need to be labelled, but otherwise you want to be clear. Now let's just mark 4 equidistant points everywhere here. As with every other graph, we want axis intercepts to be labelled. In this case, that's quite easy because those axis intercepts are the key points that are going to allow us to draw the circle. Okay, so if the radius is root 5, this is the point root 5, 0. This is the point negative root 5, 0. This is the point 0, root 5. And this is the point negative root 5, 0. And there is the graph of our circle. Centre is the origin, so we don't technically need to label it. All axis intercepts are labelled. Okay, let's have a look at example 2. Sketch the graph of x minus 1 squared plus y plus 4 squared equals 4. So remember, x minus h all squared plus y minus k all squared equals r squared has centre at hk and radius of r. So that's a k. Okay, so here h is 1, k is negative 4. Okay, the centre is at 1, negative 4, and the radius is the square root of 4, and so that is 2. Okay, so let's plot that out. Now, when you're drawing a graph of a circle, it is quite important to be a bit careful about scale in terms of you do want to use the same scale on the x and y axes. So here, for example, in this circle, if I had said, well, that's going to be root 5 on this scale and this is going to be root 5 on this scale, then when we drew our circle, it actually would have looked like an ellipse, even though it was going through all the right points. Okay? So it helps if you make sure you use a square scale so that your circle actually looks like a circle. Alright, so centre is at 1, negative 4. Radius is going to be 2, so we're going to need to go, 2 below that centre, 2 above that centre, 2 to the left of that centre, and 2 to the right of that centre. So we do just need to think about that in our scaling. Okay, so I definitely need to go down as far as negative 6. So let's let that guide the scale. So I'm going to go negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. Okay, and so I'm going to use the same scale on my x-axis. Okay, so 1, negative 4 is my centre. That's that there. okay? And we have a radius of 2, which means 2 above this point, 2 to the left of this point, 2 to the right of this point, and 2 below this point. So they're not actually key features. I don't need to mark the coordinates of those points, but I am going to draw them in to help me draw the circle shape. The key points are that we're going to cross the y-axis somewhere here and here, and so we need to calculate where those values are. Okay, so we're going to have y-intercepts. We can see that our graph doesn't cross the x-axis, so we don't need to worry about that. Y-intercepts, we let x equal 0, so we're going to have negative 1 squared plus y plus 4 all squared equals 4. So that's 1 plus y plus 4 all squared equals 4. Let's take away 1 from both sides. So y plus 4 all squared equals 3. I know some of you were itching to expand out that perfect square, but it's the last thing we want to do because we're just trying to get y on its own. We've already got 1y in the equation. So square rooting both sides, y plus 4 equals plus or minus root 3, and so y equals 4 plus or minus root 3. So that's going to be our y-intercepts. Sorry, it should be negative 4 plus or minus root 3. So it makes sense that it is, negative 4 plus a value and minus the same value, that there's symmetry there. Root 3 is about 1.6 if you just want to get a bit of a sense of where it should go. So it should go more than halfway past there and more than halfway past there. And so then we will just want to draw in our circle. Okay, it's not perfect, but it'll do. So it's 0, that's negative 4 plus root 3, and this one is 0, negative 4 minus root 3. Centre, any axis in. Minimum is centre and 1 point on the circumference, but you must always make sure all axis intercepts are labelled. So in this case, we've got centre and 2 other points. Okay, example 3. Sketch the graph of y equals the square root of x plus y minus 3 all squared equals 16. So no left or right translation. So the centre is going to be at 0, and this is, remember, when it's in the bracket here, it's a slightly rearranged form, it is up by 3. Again, if you think about rearranging that to make y the subject, you'll end up with a plus 3 at the end. So it's up by 3. Centre is at 0, 3. Radius is the square root of 4. Sorry, not square root of 4, it's square root of 16, which is 4. Okay, so again, let's have a bit of a think about what's happening here. Okay, so 1, 2, 3, that'll be my centre, but I need to go 4 above that. 1, 2, 3, 4. So that's going to be my maximum point. That's also a y-intercept, so let's mark that. That's at 0, 7. This is 0, 3. So for below that's going to come down here to 0, negative 1. That's also a y-intercept. So fortunately I don't actually need to calculate the y-intercepts because I can use the radius to work those out. Let's use a similar scale on the x-axis. 1, 2, 3, 4. So that's going to be this point out here. Again, we don't need to label that with coordinates. It's not an axis intercept or anything. But we do want to think about where it is so that we can draw in the circle. Now again, we can see we're going to be crossing the x-axis. So let's work out where we cross the x-axis. So our x-intercepts, we let y equal 0, so x squared plus negative 3 squared equals 16, x squared plus 9 equals 16, x squared equals 7, and so x is plus or minus root 7. Now remember, root 4 is 2 and root 9 is 3, so root 7 is somewhere between there, closer to 3 than it is to 2. Okay, so we're going to cross maybe somewhere kind of here and here, make sure it's sort of symmetric. Okay, let's just draw in 1/4 of our circle at a time. Okay, so that point there is root 7, 0, and that point there is negative root 7, 0. So we've got all our axis intercepts and the centre. Alright, 2 more. Give the rule for a circle with a radius of 5 and a centre at 3, negative 7. Okay, this should be pretty straightforward. We should be able to write it straight down. So we're going to have x minus 3. That's the centre at 3. plus it'll be y plus 7 squared to go down by 7. Okay, so that's our centre at 3, negative 7. And then our radius is 5, and so that's going to equal 25. So there's the equation of the circle. Question 5. Find the radius and the coordinates of the centre of the circle with this equation. Okay, so this is a bit complicated because of what's happening in here. So our general equation for a circle is x minus h all squared plus y minus k all squared equals r squared. So the fact that we've got these 2's in here, they're a problem, and we need to manipulate the equation into this form before we can correctly identify centre and radius. So I'm going to factor 2 out of that, which makes for x plus a half. I'm going to also factor 2 out of that, which makes for y minus 3 on 2 equals 24. Now if I expand out these squared, it's going to be 2 squared and the bracket squared, 2 squared and the bracket squared. So we're going to get 4 times x plus 1/2 all squared plus 4 times y minus 3 on 2 all squared equals 24. And then I'm going to divide everything by 4 so that my left-hand side is just this. Okay, so we're going to have x plus 1/2 all squared plus y minus 3 on 2 all squared equals 24 divided by 4 is 6. So now we're in the required form, and we can see that the centre has coordinates of negative 1/2, positive 3 on 2, and the radius is going to be root 6. Okay. Alright, question 6, the final one here. State the radius and the coordinates of the centre of the circle with this equation. Okay, so our equations of circles can be written like this as well. And that's about, if you think about, if we had x minus h all squared plus y minus k all squared, don't write this down, you'll run out of room. If we were to expand out the left-hand side here, we've got x squared minus 2hx plus h squared, plus we've got y squared minus 2ky plus k squared equals r squared. And these are all constant terms. If we were to combine them all together over there, we're going to have, or combine them together somewhere, it doesn't matter, but we're going to have something that looks like this. An x squared, a y squared, something times x, something times y, and a constant. Okay, so what we want to do is turn this back into this. Okay, and again, it's about creating those perfect squares, and we know we create perfect squares by using completing the square. So what we want to do is we want to focus on getting all the x terms together and complete the square for x. We separately want to focus on getting all the y terms together and complete the square for y, and then everything else should fall into place around it. Okay. Alright, so let's just get the x terms first. X squared minus 6x. Let's leave a gap so we can complete the square there. We've then got plus y squared plus 4y. Let's leave a gap so we can complete the square there. And I'm going to put the 9 on the other side, so take away 9. Okay. So we want to complete the square for x and also for y. So halving and squaring the negative 6, half of negative 6 is negative 3, squared is plus 9. That's going to be the perfect square. And when we complete the square, I usually teach you to also take away the 9. I'll come back to that in a minute. Let's focus on the y values. Half of 4 is 2, and 2 squared is 4, so we're going to need to add 4 in there. That's the perfect square. And then take away 4 to keep things the same. Now, rather than adding in 9 and taking away 9 on the same side of the equation, instead of doing that, you could add in 9 to complete the square, and to keep the equation balanced, also add 9 onto the right-hand side. So either you add 9 and take away 9 on the same side of the equation, so you've still done nothing to the equation, or you add 9 to both sides of the equation. So if I add 9 in there to make a perfect square, I have to also add 9 in on the right-hand side. Whichever way, you'll get to the same place in the end. Again, with the y's, if I add 4 there to make the perfect square, I'm going to also add 4 onto the right-hand side, and I've kept the equation balanced. Okay, so now the perfect square for x is x minus 3 all squared, plus the perfect square for y is y plus 2 all squared, and then on the right-hand side we've got minus 9 plus 9 and plus 4, and so it equals 4. And so there, once we've done that, we can now see that the centre is at 3, -2, and the radius is the square root of 4, which is 2. One other thing before we finish up, if you have your CAS available to you, you can use completing the square to manipulate that equation of the circle. If I were to go menu 3, 5, and put that whole expression in, that whole equation in even, x squared plus y squared, take away 6x plus 4y plus 9 equals 0. And remember, completing the square needs comma x, and one of the advantages of that is here we can get it to do both the completing the square for x and y at the same time by simply typing comma x, complete the square for x, and comma y to complete the square for y. And when it does that, it'll immediately complete the square for both x and y, and then obviously leave whatever's left over on the other side of the equation. And we straight away get to that general equation for a circle. Okay, so exercise 4D is the practice here for equations of a circle.